this is one ring, this is another ring, this is another ring. And we discussed in our previous videos that these rings, basically this ring represent nothing, just the peak in XRD graph. This represent one peak, this represent another peak, this represent, you know, when you look into the XRD, you will see the highest peak, the sharp peak. So that will represent this sharp ring. If the peak is decreasing in intensity, so you will see here a less intense ring, right? So now we are going to find how to find the interplanar spacing between two planes, or in other words, how to index HKL value to each ring. Once we assign HKL value, then we can easily find D. Once we know HKL value for ring, for each ring, we can easily find D. Let's to find how we can find the this D value, right? If you look into this this scale here, this is, let me zoom here, this scale is 2.00, mean 2 in 1 over nm, nanometer. This is because we are talking about reciprocal lattice, so the unit is 1 over nm, 1 over nanometer, right? When you want to convert this in, so we will talk about a real space, but this is now we are talking about the reciprocal space. This is how I assign the HKL value for each ring. And if you look into this pus ring, the HKL value is HKL. If you look into the XRD, so this represent the pus 110. You see here 110. This is basically represent the pus peak here, because these two are same material. Maybe some other we don't have some other peaks, but most of the peaks, the major peaks will be reflecting here, right? Now let's to know how we find. First of all, we need to measure the dia of the ring. Basically, this is let me delete this one now. You can see here that how to find the dia. This is the dia of the ring here. Use MHJ tool or any tool. This you see here, I just draw the scale here, and if you look into this here, so this is almost 4 nanometer, 4 nanometer this dia. So when we measure the dia, so this dia basically 2 radius and it is equal to 4. Now the unit is in 1 over nm, because we are talking about reciprocal lattice, right? So the dia is 4 nanometer, so the radius become 2 nanometer, right? Now we know there is a relation between the reciprocal lattice and real lattice distance. So they are inversely proportional to each other. So we can see that the distance between the two planes is 0.5 nanometer. Very easily we can find the spacing between two planes from a SAED pattern, right? Let's suppose if we have now this material 10x side, and we know that we know from the literature that the 110 plane is correspond to this distance, because we know from the literature, right? So this is how we find the HKL values very easily. Look here, we just measure this dia of the ring, and it is in reciprocal lattice, and from there we find the radius. There is a relation between the reciprocal lattice and real lattice. This R is basically the distance between the planes in reciprocal lattice. This D is when we are talking about the real lattice. We are not talking about the reciprocal lattice. So this is the real distance between the two planes. There is the relations. So once we know R, we can easily find D. Now we got the D value. D value is 0.5 nanometer. Now compare the literature of this material, for example the 10x side, and you will see that the distance between the two planes is this D, and that correspond to this peak HKL plane, right? This is how easily we can do, and you can repeat the process for all rings to obtain the D values and compare it with the literature. Okay, the pus ring is usually more intense, as I explained that it is related to the pus peak of the XRD, right? So in this way you can index the SAED pattern and assign each ring in HKL values, right? In other words, you can find in which crystalline form your sample is. This is how we find the value of D, or we index the HKL value in a SAED pattern. Okay, right? This was all about how we indexing the ring into the HKL value, right? If you look into the theory here, so we also indexes this plane, this peak to some HKL value, because this means that why this HKL value, it is very common. This means the diffraction is basically in 3 directions, because if you look into the crystal material, it is in 3 dimension. So it is in X direction, Y direction, or Z direction in those worlds. So this is basically the diffraction phase is basically. So you can see here that this peak basically represented by a certain value of HKL. So this peak is represented. So similarly here, this ring is also representing by certain value of HKL, and this is how we index this value. The method we explain here, and you can easily index the HKL value to the rings.